So I'm not sure how long I'm supposed to go. Brian said less than 5 hours. At the end, we do offer a test. So if you brought a number 2 pencil, you're allowed to use a slide ruler or a calculator at the end, just to cover the basis of, fairness. If you didn't bring that, then, follow closely, because we're going to be covering Joukowski's wave equations and the method of characteristics. So we're going to be discussing another beer. Yes, there you go. So we're going to talk about water hammer. So who in the room has ever closed the valve? Raise your hand. Woo-hoo! I'm making the correct presentation. So I always say to my kids, it's like, I hear, like, what in the world was that? Somebody left the hose bib open and the dishwasher just kicked on the solenoid, sent that pressure transient through my house. It went through the cross connection control device, allowing a high pressure wave to enter into the hose that's out in my yard, expanding with pressure. When that opened up, there was a high pressure wave that came back and slammed the valve closed. And then my house goes, "Rrr." Who lives in an old house and knows what I'm talking about? All right. So from an engineering standpoint, we're like, I can take care of this. I need some thermal expansion. I need a surge vessel. I need my kids to close the valve slowly. Right. So, but what about that dishwasher or the washing machine? Or if we're in a high-rise hotel downtown, and it's like every time they do a load of laundry, that 2-inch solenoid valve slams shut and the whole hotel goes. So this is surge and water hammer. What we're going to cover today is, how does this apply from an engineering standpoint? Most engineering firms are looking at steady state flow. What is my pressure when I kick on my pump? Is my pump pressure, flow, everything set? But it's in steady state. Steady state is like everything working perfectly. Now, who lives in a perfect world? Oh yeah, there we go. Okay. But in reality, it's like, wait, somebody just closed the valve. Somebody turned off a pump. We have some electrical engineers here. I heard that every once in a while, there's a power failure. How many have ever experienced that power failure before? So if I'm running my pump and I have a beautifully designed system, right? Pumps designed perfect. I might even have a pump control valve to manipulate the starting and stopping of that pump in the system. And I have specific flow, pressure, velocity going out into my system. And then we lost our power. And guess what happened to my pump? He's like, oh, I got a little inertia here, right? So I come to a stop. But guess what? My water over here doesn't know when to stop. It keeps going, okay? So it's rushing out. And at the discharge of my pump, they're like, oh God, I'm in a vacuum condition. It's like, because that negative wave went out and I'm pulling a vacuum in my system. And everyone in the room's like, well, that can't be good. Well, what if that negative pressure wave going out dropped below atmospheric pressure and we start pulling a vacuum on our piping system, which allowed that pressure to drop below atmospheric pressure? And you know that little leak over there, you can see it in the road. It's always there. Like, I clean my tires when I drive by, right? Well, that little leak over there by the bayou, well, now I have this negative wave going through my piping system. And it's like, well, hello, friend. I love some good bayou water. Why don't you come into my piping system with me? Because I'm in the vacuum and I'm going to suck you into my piping system so that we're going to have better tasting water. Who's with me? Who wants some good bayou water in their drinking water system? No takers. So as engineers, you're like, ooh, we don't want negative pressures. How are we going to solve this problem? So we look at computer surge modeling. It's like, I'm going to manipulate the starting and stopping in this pump. I'm going to put in variable frequency drives. I'm going to have the best possible system design in my water system, my wastewater system, my chemical process. If I'm pumping crude oil from the Gulf of Mexico to Port Fourchon. That was a shout out for Port Fourchon and shout outs for Port Fourchon. What is that pressure transient going in the system, and how can I design my system to protect it, especially from the negative pressure wave? Now, when you look at your piping system, it might have a marking on there that shows the maximum allowable working pressure. And we all know we have safety factors within our design. But where does it say my piping system can handle a full vacuum? And can my piping system handle a full vacuum? If you ever Google and this is one of my favorites, is that rail car, they're draining the rail car and they're not breaking it to atmosphere. And it goes, it's fine, it's fine, it's fine. It's flat as a pancake because that vacuum pressure that was created when you were draining that tank is just like your piping system. If you turned off your pump and that negative wave goes to a vacuum, you end up collapsing your railroad car is one. What if you collapse your whole piping system? It's like, that's not going to be good, right? So we have to protect our piping system. And if we look at, say, potable water or in a chemical process, what is the vapor pressure of my chemistry? So in potable water, we have state laws and guidelines that we don't want our water pressure to drop below 20 PSI. But what if our pressure dropped to a vacuum or a full vacuum? We would run the risk of having a cross connection within our system. How are we even going to know this happens? So let's go back to our pump. Pumping 1,000 gallons a minute. I got 90 PSI. I'm living life large. Life is good. I turn off my pump. Negative wave goes out. I'm looking at my pressure transmitter or my gauge. Love a good gauge, right? Pressure gauge said, oh, the pressure dropped down to 32.5 because I can see that in the pressure gauge, right? And then it came back as a high pressure. Or my pressure transmitter, it is so smart. It's looking at the pressure once a second. So everyone thinks that's fast. That's amazing, right? I'm looking at the pressure once a second. Turn off my pump, 90 PSI, drops down to 33.62548 PSI. Now, that was a capture of that pressure. Let's talk about the pressure wave. So, we were flowing 1,000 gallons a minute, 90 PSI, and then we stopped. Well, we've created a shock wave within our system. And now, depending on your piping material and the wall thickness, you've created a shock wave. So that wave could be traveling through your piping system at 3,280 feet per second. This is on the test later, remember that, all right? Because it's metric, 1,000 meters per second. It's like, that's pretty fast. It's like, 4,000 feet per second, and I'm recording it once a second. I'm not recording anything. So you have worthless data from your pressure transient. You have this negative wave going down the piping system. And then what happens? Negative wave. Sorry, cameraman. We're following the wave. I'm going 4,000 feet per second. And I might go up into that elevated storage tank or into this chemical reactor. All right. I went out negative. Guess what's going to happen? I'm going to reflect back, and I'm coming back at you, pump, because you just tricked on me, right? And you're like, you and all my friends were going this way. You went this way. Now we're coming back, right? So here comes a high pressure wave coming back. It's like, wait a minute, the check valve is still open, right? And you're thinking, geez, what in the world was that sound? Well, that was your check valve slamming shut. So everyone in the room's like, everyone's seen a check valve? Okay, right? Oh, how are we going to get our check valve to close faster, right? So it's like, that high-rise building I built downtown, I turn off the pump, and then kaboom! boom, this big power surge comes back and the check valve slams shut. It's like, how in the world am I going to solve this problem? Thinking to myself, what if we put some weight on our check valve? Okay, that's going to get it to close faster, right? Who's with me? Who's ever seen an outside lever and weight on a check valve before? Okay. Yeah, it might even be in your specifications. And it's like, if you gave me 40 hours, I'd go into more detail. But let's talk about gravitational acceleration. Is it the weight of the body or the distance it's traveled? So is that weight actually doing anything to increase our closing time of our valve? No. Okay. So we're like, ooh, spring, right? Let's put a spring on our check valve to exert its own mechanical force to pull the valve closed faster. Okay. So the idea is that we want our check valve to close before that wave goes out and comes back at 4,000 feet per second. If it doesn't, and I got some examples, I had a pump station in San Francisco, sewage lift station. I was pumping 10 PSI. The engineer who designed the system and did the surge model, steady state, 10 PSI. Negative wave on a pump trip, pressure dropped to 2 PSI. High pressure wave came back in the surge model, pressure was 17 PSI. And it went back and forth and everything was beautiful in the surge model. In reality, we're here to do startup. It's like, yeah, this is going to be a beautiful pump station, 30-inch check valves, outside lever, weight, cushion on the check valve, 54-inch steel line. Okay. Pumps are running, life is good. They turn off the pump, negative wave goes out per the model. High pressure wave comes back, just like the model. Check valve. Check valve was a little slow. So the check valve's like, I'm trying to close, right? This wave is hitting me and I'm trying to close. And it lets some water by. In this case, it's wastewater. But, you know, water sounds better because we just ate dinner. It's getting a little flow by it. Oh, I'm going to close. It's good, right? And then I'm going to finally go closed. And then everyone ran out of the pump station because when the check valve allowed for a reversal of flow and closed, the pressure hit 273 PSI. Okay. And then what's to follow? Well, where are we over here? Oh, there's negative wave and then a positive wave. Same thing with closing a valve. I am a positive wave. Now what's going to happen? Now I'm a negative wave going down the piping system. But 54-inch pipeline, I'm minus 10 PSI vacuum. Guess what the piping's doing? Oh, it's a vacuum. Oh, pressure. Oh, vacuum. So the piping system was like, ooh, I'm breathing. So has anybody seen this happen in a pump station? You're like, I don't want to see that, Frank. Right? So we're going to start off with a video. I'm going to start off with finding my mouse. No. Where's the escape? Perfect. So I want to show the video first. It's like, I got my mouse. Like that. So this is a large raw water piping system, and someone had the audacity to close the valve. So what you're going to see is an upsurge in pressure followed by a negative wave, just so you can see the cause and effect of a change in velocity within your system and why we need to do computer surge analysis and modeling of our system. High pressure wave, valve closed. Oh, that doesn't sound good. So from engineering standpoint, we need to dramatize it. So we're going to speed it up a little. So now you get a feel for that wave. Now you get a feel for that wave traveling back and forth in your piping system, traveling at 4,000 feet per second, in the cause and effect of your piping system. And everyone in the room's like, who's the structural engineers? They can solve this. We'll just anchor everything down and it won't go anywhere, right? Right? Or do we design around the system? It's like we're still dealing with that valve closure. We've all closed that valve in our system. What's the solution? We can go through it mathematically using Joukowski's equations, very simple math, and see what that change in velocity is within our system when we close the valve. Or we can use computer modeling software, entering everything, and I mean everything. We want the elevation. We want the pipe diameter. We want the piping material. We want to know everything about the pump. It starts with the pump, right? And it's like, oh, wait, hold on. It's a vacuum thing. I got a solution. We'll just put an air vacuum valve on there. That'll do it. I'll put an air vacuum valve on there and I'll not have any vacuum condition. Who's with me in my design? We're going to love this, okay? So this was a flaw in the software going back in 2006, designed a beautiful pump station, force main. It's like, oh, this is good. I love this one, right? And it's like started up and the pipe goes, I'm like, open up, air vacuum valve. Come on, open up, right? Well, the software said the air vacuum valve, the vacuum valve is going to open up instantly. Okay, it didn't open it instantly. There's a reaction time. I got to get the water, the wastewater, the cyanide gas out of the air vacuum valve. I'm kidding, right? The liquid has to leave the vacuum breaker and it has to break the atmosphere. And let's just say it's the best possible vacuum breaker out there in the world, and it's going to open up in half a second. Oh, that's pretty cool. Where's my pressure transient wave in half a second? It opened up and broke to the atmosphere, except for, oh, wait, you're already 2,000 feet. That negative wave is already going 2,000 feet down my piping system. It's like, oh, well. So case in point, you're designing a sewage force main, put in a default. It'll give you a better feel for your surge model of what's happening with that air vacuum valve. From my standpoint, my default is 1 second. You talk to operators out there, they're like, yeah, it's probably not going to work. We're forever out there. We have 8 guys, people, excuse me, 4 trucks. We're flushing out our air vacuum valves. You know, they're always full of baby wipes. Right? So it's like, will it work? So is this my best possible design of my system? It's like, so if I was designing a system and I'm dealing with this negative wave, it's like, how do I control the inertia or the change in velocity within my piping system? It's like, I know up in Shreveport at the old water plant, they have a really good looking flywheel. Who's designing a system with the flywheel? That's it. It'll add to the inertia of our system and keep the line positive. Who's with me? Who's designing systems with flywheels? Good job back there. Yes, it is a solution. Okay. What's another possible solution? It's like, oh, must give energy to change in velocity of the system. It's like, I'm going to put in a surge vessel. So who here is from New Orleans? Do you go by the, oh, wow, everyone, this could be the New Orleans chapter of Louisiana Professional, wait, never mind, it is. You go by the Carrollton water plant, you're like, that's a good looking elevated storage tank. Like, they have all these ground storage tanks. Why do they need those 2 beautiful, beautiful elevated storage tanks right at the water plant? Anyone know? They are to give energy to the change in velocity when they have a power failure. Okay, so that's part of the solution in the design. Now, what if you're designing a gravity system, say for drainage water or sewage? Oh, there's no pressure transients. You know, that's not an issue. It's gravity. It's like, I'm slowly going down the street or the ditch. It's like life is good, except for when we have a storm surge, which, you know, in New Orleans, that happens all the time, right? So has anybody ever seen the video or driven through Lakeview and you're like, wow, who designed this road? Did anyone design that road here? I'm so sorry. It's like, I'm like, maybe if they didn't weld the manway covers, you know, so they don't blow off, you wouldn't have a big upheave in the road. And you're like, well, it's a gravity drainage system. It's like, why would we have an upheave? It's like, I say we watch this video and then everybody watch where you park your car. So everyone in the room's like, no, could you excuse me for a minute? I got to go move my car. So what's going on there? We're having a class today on pressure surges and transient analysis. It's like, how in the world does that even happen, right? So we get into something I can't solve. Sorry. It's called two-phase flow. So I have a partially filled line, starts to rain, fill up my piping system. I have some trapped air in there. That air pocket collapses, accelerates, moves, and is creating pressure transients or surges. So I'm getting these geyser flows in my drainage system, and it's devastating. So there's certain areas. How do you solve a problem like this? It's like, don't weld the manway cover to the street, because that pressure surge is going to destroy your whole road with that upsurge in pressure. In some cases, we look at this and try to model it, but we can't model it because this is a two-phase flow. My software is like, tell me about your specific gravity. Tell me about your fluid. It's like, I can model a negative wave going out and adding air into the piping system. And where does it go from there? I don't know. Okay. But as you can see in that video, it collapsed, it created a pressure wave, and it came back and bam, hit the car. Okay. So we're going to talk about why we're here today. This is a math class, right? Wait, no, this is a dinner fun. We're supposed to be entertaining, right? So you're like, how am I going to manipulate that pump? And from an engineering design, be it I'm pumping crude oil, or I'm filling up a super tanker or a rail yard, or just water going out into your distribution system. So the manipulation of a pump control valve. A pump control valve is going to look at your pump, and you might design, let's start off with something simple, a sewage lift station, and I've got 5 pumps. Love to model, pumps in parallel. And of course, from a surge modeling standpoint, we are very pessimistic. It's like, what is the worst thing that could ever happen? What is the maximum flow, maximum velocity and pressure in the system? And then electrical engineers, we're going to have a power failure. Okay. So I'm going to design for the worst case scenario. And the electrical engineers in the room are like, power failure, what if we have a separate electrical grid that we could put in a switch gear and just grab the power from over there and keep our pumps running? Is that a solution? So I was working on a project in Texas, and they're like, we can just tie into this electrical grid. We'll have a switch gear. It'll switch over. We won't have any pressure transients. I was like, call me. So a month and a half later, they're like, hey, can we talk about this water plant design again? I'm like, you blew it up again, didn't you? They're like, you didn't see, this time we got world news. We're on world news. It's like, turn to channel 4. Okay, so how do we manipulate the starting and stop of our pumps? And if I'm designing a sewage lift station, my worst case scenario, I'm running 5 pumps. It's raining outside. Everything's going to my sewage treatment plant with this beautiful, pond, interceptor that I have in the design for that, crazy rain flow that we have. Okay. Perfect design. Someone like me comes out there and looks at the model. Like, the worst case scenario, let's pump the trips and prove the design. The next day they're running the pumps. They're like, well, we only need 1 pump when it's not raining. So it's like, start up that 1 pump. Like, I don't have a flow. Something's wrong with this pump. The pressure's wrong. It's very low. I have no flow. I have a partially filled line. So it's like, system worked great with 5 pumps, doesn't work at all with 1 pump. because I have a partially filled pipeline. What's the solution? Every project you're working on, remember this. Your customer wants a 48-inch force main. Beautiful. They're going to love it. Okay. This is a great engineering project. But hey, could I get a 16-inch pipeline going alongside that? Because when you're running one pump or two pumps or three pumps, that 16-inch pipeline is going to love this. That 48-inch pipeline is going to fight you all along the way. So we're here today to protect our pumps. So we look at a device like in this picture where I can manipulate the pump from a starting and stopping standpoint. Now, wastewater pump stations, I want to start at 100% and then ramp it back down if I have variable frequency drives. It's great because I need some flushing action. I'm like, give me some flow velocity. Let's get this going. And then, ramp back down. When I go to turn off the pump, as we discussed earlier, that change in velocity in the system, if it happens too quickly, I'm going to go negative. So using Joukowski's wave equations or using a surge modeling software, we're going to calculate how slow we want to close the valve. So we put in a pump control valve. This is beautiful. It's going to slowly close off that change in velocity with the pump still running. When the valve is 99% closed, or looking at the pump curve, what is my minimum flow? What is my pump like? Am I running other pumps in the system? Then I'll turn off the pump. And in doing this, you'll see in your design, when you have multiple pump stations, and I was working on a project in California again, Southern California, many vertical turbine pumps. Every time they turned off one pump, they get a low pressure alarm on the suction side, which shut down the whole pump station. And it was like, oh, really? They're like, we don't know how to solve this problem. I was like, your pressure transmitter. We had to throw something into the electrical instrumentation engineers in the group. Your pressure transmitter sees that pump stop. When I turn off the pump, what's going on the discharge side of the pump? Well, I got a negative wave going out and a high pressure wave coming back. On the suction side of the pump, we're looking over here. It's like I turn off the pump. Well, that flow of water is still coming to the pump. The water over there didn't know. We just turned off the pump. So we have an upsurge in pressure, okay? Which is then going to reflect back as a negative pressure. So every time they turned off their pump, their instrumentation is like, oh, we're pulling a vacuum in our piping system. It's like, no, it's the pressure wave in your system. Put in a little dampener, buy your pressure transmitter, and then you'll stop getting these false alarms, and it's going to cost a couple $100. You're about to try to figure out this problem and have a $10 million engineering contract. Oh, wait, no, I didn't say that. Like, no, we're going to have to investigate this for the next 6 months to resolve this issue. Sorry. Because we're in a room of engineers, I can say that, right? Otherwise, controlling that pressure transient going into the pressure transmitter resolves the issue. So we discussed pump control valves, and we can get into computer modeling and why this is so important. But it's like, we go back to the same thing. It's like, oh my goodness, I'm in New Orleans. I'm running my high service pumps. Life is good. And then I have power failure. You're like, you already told us you have a surge vessels. Those two beautiful vessels out there, they'll protect us, right? Who's with us? It's like, yes, but I still got to close the check valve or the pump control valve. It's like, as I discussed earlier, it's like, please check valve, please close fast so we don't have a secondary transient event happening in our system. So in this design, there is a hydraulic piston accumulator with stored energy. And it's like, valve, I am here to help you. If you have a power failure, you'll switch a solenoid and I'll drive the valve closed. But it's like, oh, wait a minute. How fast do I need to close? Well, in the case of New Orleans, it's like, I need to close really fast because there's a surge vessel right there and it's going to send energy back at me. Like immediately, we're not going to have a transient wave go from the water plant all the way to New Orleans East and come back. Oh no, it's sending energy back immediately. So I need to close this big old ball valve as quick as possible, but I don't want it to slam shut. So I'll design the system with the two-phase closing. So you design the perfect system. Everyone's listened to me because you get continuing educational hour for this, right? So everyone's going to listen to me. Except for I was doing this system and we were using water from a paper mill used to frack some wells in northern Louisiana. I don't know where this was taking place. So this is how you're going to start your pumps. This is going to have to shut down your pumps. Our system is designed to maintain a constant flow rate and pressure on the suction side of this multi-million-dollar injection pump that's going to bring the pressure up to 8,000 PSI so we can hydrofrack this well. Like, okay, this is great. But because you didn't put in your surge vessel yet, and the station is not running per design, this is how I want you to operate the system. Yes, sir. Yes, sir. We're doing this. It's beautiful. I spent 3 days there. Everybody in the facility is listening to me, and they're like, God, can he just stop talking about pressure transients for a minute? So the next day, I left. That afternoon, they sent this picture. So the paper mill's like 7 miles away. They're like, we're not going to listen to them. We're just going to turn off the pump. It's like, switch off. We don't need to manually slowly shut down the change in velocity of the system. So they just turned off the pump. Negative wave went to a full vacuum. So basically, what happens to water when it's exposed to a full vacuum? It starts to boil. So negative wave goes out, hits the back of this 70,000-pound skid, blows out the back of it, wave reflects back. Remember, negative wave out, high pressure wave back, cavitation, implosion. They ripped apart their 24-inch piping, ripped apart the expansion joint, and blew apart their piping. So the case in point is, yes, this is something we need to learn about, what can happen within the system, and tell your kids, do not close the valve in the faucet too quickly. Oh wait, my son's here, so I had to throw that in. He's like, God, he keeps telling me that over and over again and over and over again. So to give energy to your change in velocity of your system, you might consider putting in a surge vessel. A surge vessel might be like in New Orleans, those elevated storage tanks. It might be a hydrodynamic tank. It might be a bladder tank. It might be a bladder tank with gas in the bag or liquid in the bag. It depends on your design, your system. This might be water. It might be wastewater. It might be crude oil or diesel. So it is also an ASME pressure vessel that needs to be inspected and maintained. So here's a customer is like, oh yeah, we have a surge vessel. We don't have any water hammer problems. And then they send me a picture. Well, we didn't maintain the gas charge properly. We lost our gas charge. We had a transient power failure and we blew apart our tank. So you would not want this to be your design either. So we've been talking about New Orleans Sewage and Water Board because, we're in New Orleans. So here's a picture of their pump control valve with a Rexa electrohydraulic actuator. It's still closed. So in normal conditions, starting and stopping those beautiful old 100-year-old pumps, we're manipulating the starting and stopping of that pump. And then if we have a power failure, which we have all the time, that surge vessel in the background will give energy to that change in velocity, and the pump control valves will close based on the surge model. So we look at this and we don't rely just on the pressure transmitters with regard to the proof of design. We put in high-speed pressure transmitters so we can see the cause and effect of turning on and off that pump within your system. And we're recording that pressure transient at 100 times a second. So we can see that negative wave going out and coming back. Now, if you're designing a system working in a chemical plant, this is a good starting point from analyzing a system from a pressure surge, transient, water hammer, whatever you'd like to call it. With regard to engineering design, it's been pretty much open. There's no standards committee up until last year when it comes to computer surge modeling and design. With the Hydraulic Institute, we started a pressure surge committee this year to address standards, operation design, software, and more details in the system. Why? Because we don't want our piping system to look like this. This is a 16-inch PVC piping system. Every time they turned on and off the pump, negative wave would travel down the piping system, pull a vacuum, and eventually the piping system failed. When we're designing a system, it is also very critical to look at the pump curve that you designed the system on. You're like, well, what do you mean? We've been talking about pump trips. Well, what if I'm starting up a vertical turbine pump? Should I be concerned with the startup surge? And it's like, yeah, of course. And it's like, well, in the software, it's really difficult. How do you model that? It's like, you just can't, like, I got to be in steady state to look at that transient event or the change in velocity in the system. So from a computer modeling standpoint, run the pump, turn off the pump, then turn the pump back on so that your computer, supercomputer is like, okay, we're in steady state. This is good. Okay, you turned off. Okay, this change in velocity is great. We've got the inertia right in my pump. The pump curve is correct. I got 10 points in the pump curve in here. We're fine. Okay, here's the negative wave. Okay, the length of the pipe is this. It's like, this is beautiful. Okay, I'm off. I'm in steady state. Okay, I'm going to turn back on. So now the software is like, okay, what's going on when I turn the pump back on? So you can look at that startup surge of the pump. And again, my pet peeve, vertical turbine pump. If this is a water well, this is a water well, okay? I have an air vacuum valve. I have a static water level down like 40 feet. I turn on my pump, and now I'm going to move the air out of an air vacuum valve. And what's my pump and motor doing? Well, this is an easy job. It's like, I have no back pressure. I'm just moving air. I'm going way over here to the right-hand side of my curve. It's like, I have no resistance. This is good. I'm spinning fast. This is crazy. And then all of a sudden, bam, I start pumping water. Guess what happened? My system that's designed for 90 PSI just got hit by 463 PSI when I started up that pump. And you can see when we're in steady state, it's like, oh, it's all good. The only problem that happened here was, my piping didn't make it through the 463 PSI. And of course, everyone in the room knows this is the contractor's fault. It's the contractor's fault, okay? It's like, so the contractor fixes the pipe, starts it back up, rips the flange off the pump. It's like, not only is it the contractor's fault, any contractors here, I'm so sorry. It's the pump manufacturer's fault. It must have been a faulty casting. They fixed the pump, put it back online, start up the pump. They ripped the 45 where the piping goes into the ground. They're like, all right, maybe it's not their fault. The scenario was understanding the pump, understanding that startup surge of the energy. I was at a pump station to do startup, and it was like beautiful pump station, 700 PSI was what we're pumping. And that was my maximum head pressure. I'm like, no one shared with me the pump curve. I always want the pump curve. I want the as-built pump curve. So they're like, whatever. I thought you were the surge guy. It's like, you know, what's with the pump? I'm like, looking at the pump curve, I'm like, we're not starting this up today. Like, what do you mean? I'm like, your left-hand side of this pump curve, it's going to be 950 PSI when you start up this pump. They're like, what do you mean? I'm like, look at the pump curve. This is a vertical turbine pump. What's going to happen when you start up this pump is all your safety relief valves are going to go off. Okay. And guess which way they're pointing? They're not pointing down. They're not routed. You're going to kill someone because they will open up. So it's like, step one, when I get involved in the project, do you have a surge model? Can you send me the model? Can I run it in my computer? Before I go to start that up, I want to know what's going on within the system so you don't have a situation like this. So that's the fear factor in engineering 101. When we're in running a water system and it's like, I'm just going to turn off the pump. Everything's going to be fine. Well, in this scenario, potable water, 70 PSI. When you turned off the pump, it went from 70 PSI to 6.1 PSI. Potable water. What are we supposed to maintain? A minimum pressure of 20 PSI. Is this a good design in the system? No. How would you know if it's working correctly or not? You have to look at it at 100 times a second. So again, here's a potential risk from a municipal water system. We're getting into the 40-hour class. We'll skip ahead. Now we're talking. You're like, well, wait a minute. That's way too many graphs. So my mentor was Dr. Don Wood from the University of Kentucky, who developed the software I use, which is KY Pipe surge modeling software. And years ago, there was a 72-inch pipeline. It was designed, and it was a gravity flow system. It had a 72-inch valve, and they designed the system so the valve would close in 30 minutes. In the computer model, the transient monitoring equipment, the design was gorgeous. There was absolutely no pressure transient. They did not exceed the pressure rating of their piping system, nor did they drop into a vacuum state. The valve closed in 30 minutes. Electric motor operator, stepping motor. Close, 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 close. Beautiful. Until somebody, and it wasn't the electrical engineer because he designed it properly. It was a disgruntled electrician. Does anyone know one of those? Pulled out the jumper. They closed the valve. The valve closed in 5 minutes. You're like, so, right? So the blue line is the valve closing in 5 minutes. You're like, oh, that's beautiful. Oh, you're still under 200 PSI. That's great. Except for when it closed, then remember, I'm closing the valve. I'm building up the pressure. Okay, the valve closed. I've gotten to that high pressure mark. Now what happens? Oh, shit. Excuse my language. That wave is going to reflect back out negative. And in this case, it went out negative to a full vacuum. And when it did that, it basically did $30 million worth of damage. Okay. So my mentor's like, close the valve in 5 minutes. Well, we already know what happened in closing the valve in 5 minutes. So using computer software in a 2-stage closing, I'm able to close the valve very quickly and then slow it down based on the critical velocity and the wave speed within the system. So then I get the purple line. You can see I close the valve very quickly, and then the second stage, I slow it down, keeping the high pressure lower and the low pressure higher to protect the piping system. And you can see this graph here is based off of the change in velocity and the velocity change within the system based on the surge model. So within the software itself, we're like, ooh, active valve. Now, you might think, I'm closing a valve. Well, I got a water system. It's like, there's a whole bunch of water meters and all that. Why should I really be concerned about my municipal water system and someone slam and say a 6-inch valve closed? How could that ever happen? So you've designed a perfect pump station, pipeline, everything is beautiful, steady state is fine. And unless you're looking at pressure transients coming back at you at 100 times a second, you're like, best design ever, right? And then, down the street here, there's that really big building and they have a reduced pressure backflow assembly. And then there's a detector check. And every month they test their fire water system, or that chemical plant over here. Well, that's another parish. So, but it's close to here. Big chemical plant, uses a lot of our potable water. And, our pressure is only like 40 PSI down there. So they have a booster pump, right? So they're in there taking 1,000 gallons a minute of our water, and, life's great. They're a great customer. We make a lot of money off of them. It's really good for us, except for when they turn off their pump. And you're like, well, isn't that normal? That's in our design. But coming into that chemical plant, I have a reduced pressure backflow assembly. I'm flowing 1,000 gallons per minute. And then I stop. Guess what happens? Kapow! That pressure in your water system might go 40 PSI to 400 PSI. So your municipality is like, and this is your client, they're like, God, I don't know what's wrong with this system. And it's that customer that's destroying the municipal water system. So how do you solve that problem? And again, through computer modeling, analyzing, look at that pressure transient, and to solve that problem, you got to control the change in velocity within the system. So this is where we look at surge vessels, pump cycle control vessels. How do I give and receive energy? How do I accept that energy? And it starts with computer modeling of our system. I'm skipping ahead because I promised you some math. And, I'm not sure how long I'm supposed to go, but we always need math to back up what we do. So everybody in the room, take out your slide ruler and your number 2. We forgot the paper. Frank, I told you we should have brought the paper. So we're going to keep it easy. Just got an 8-inch valve here, right? I'm in a building down the road. My piping system is 1,640 feet long, 8-inch piping system. I got an 8-inch valve and I'm going to close it. Because you came to this class, you're like, I'm going to close this valve slow. I'm going to take 20 seconds to close this valve. So let's do the math. We're going to calculate the loss of head factor in the piping system, the hydraulic resistance of the pipe. I said the piping is 1,640 feet long, 8-inch line. K factor is 50. Now, remember, we started this off with that damn wave, okay? So that wave is like, my piping system is 1,640 feet long. That wave's going to go out, and then it's going to come back. So 2 times the length of the pipe divided by the celerity of the wave. The celerity of the wave is the velocity of the wave traveling through your piping system. Okay, again, piping diameter, wall thickness, piping material. We can calculate the wave speed within our system. So in my piping system that's 1,640 feet long, that wave's going to go out and come back in 1 second. Because, I am old. When I went to college, we didn't have a computer. We had to do everything by hand. Now the software is like, oh, here, we can calculate the wave speed for you. Life is good. I would like to go back to college now, please. So here we are. Valves close, the wave speed out and back is 1 second. I'm going to take 20 seconds to close my valve. My KN factor is 1600. I'm substituting the change in velocity to Joukowski's equation. I'm adding in my operating pressure, which is only 42 PSI, gravitational acceleration, and I come out with the pressure went from 42 PSI to 129 PSI when I closed that valve in 20 seconds. So mathematically, using Joukowski's equation, we can do some rough calculations. This is great if you're just looking at, say, a pump control valve, or you are in the field. I want to close this valve. So what happens in reality? I got an 8-inch valve. I'm filling up a ship, and I got someone standing there waiting. It's like, row is full, row is full. He hooks the butterfly valve with his boot and kicks it closed. I got to design a system now with a 2-second closure. It's like, because I didn't calculate the boot theory. So we're all tired of the math. I had a cerveza, das ist ein Bär, das ist gut. Let's do computer software. It'll speed things up. So I enter into everything about my piping system into the software, and now I can simulate many different things within the system design. When I close the valve in 20 seconds, you see that upsurge in pressure in the red line. And again, using same Joukowski's equation. If I take 60 seconds, this would be the green line. You're just like, ooh, that's a lot better. We should close the valve in 60 seconds. But wait, I got the person that's like kicking the valve closed, okay? Or that reduced pressure backflow assembly going into that chemical plant or that high-rise downtown when they turned off their pump or they closed the valve and slammed that valve closed. Now I get a 2-second closure because I slammed the valve closed in my beautiful pot of water system and I'm only operating at 42 PSI. The pressure hit, what, 564 PSI, 65 PSI. It's like, I can't design my piping system for that. What do I do? What do I do? Well, it's high pressure. I'm going to put in a relief valve. Who's with me? Who wants a relief valve? Right? So we got to look at, in the modeling software, everything about that relief valve. When I hit that high pressure and input the high pressure into the model, there's a couple things that go on. I opened my relief valve. And then the negative wave goes out because remember, it's traveling back and forth in my piping system. It's like, relief high pressure wave. And guess what that wave did? It went back out negative. It's like my relief valve was like, guess I can close now, right? You know, the high pressure wave left. The valve goes closed. I'm good. Wait, second later, high pressure wave comes back. So this is where I'm illustrating the pressure transient as it's going back and forth in this poor relief valve. Open, close, open, close, open, close. So the reaction time of your relief valve is critical in this type of application. Yes, you can size your relief valve. And in many cases in large diameter piping systems, like I was doing a crude oil pipeline, I needed my valve to open up in a fraction of a second and then close slowly. So I didn't get this pressure transient going on within the system. So we look at different types of relief valves. This is a mock valve that I was in the Netherlands last month and looking at how fast their safety relief valves could open up in the system to see if this is a potential solution to some of our designs. And it's all about reaction time. And I could go on about that for about 40 more hours, but we don't have 40 hours. The next is I have this high pressure wave. What if I put in a surge vessel to accept the energy? So I'm going to have a specific volume, a gas charge. When I exceed the pressure limits, I'm going to compress that gas charge to cushion the pressure wave. So I'm going to use the software to calculate the vessel size, the diameter, the gas charge, and to cushion the system. So in simple systems, that's fine. In other cases, I still have to contend with a high pressure wave coming back. If I'm saying pumping over a mountain or a long distance and I have a high pressure wave returning, I might also have to rely on a relief valve, or I might have to cushion the flow coming back into the surge vessel. But a surge vessel is a way of accepting energy. A surge vessel can also give energy when I turn off the pump. It'll give energy to that change in velocity so that we can keep our piping system positive, so that we do not go into a state of cavitation, or we're not respecting the minimum operating pressure of your piping system. Again, utilizing software, and it's again using a gas law of applying that specific gas volume and compressing it. And just a quick video so you can see what's going on within the vessel itself. This is a higher pressure, lower pressure, and when I turn off the pump, I am here, I'm giving energy to that change in velocity based on the pressure change, and my gas pressure is expanding. So we look at the polytropic constant based on the length of the pipe and how quickly I need to give energy. So we're also calculating the polytropic constant within that gas for our piping system, depending on what's going on in the surge model itself. So what's our time frame? Wrap it up or keep going? I'm like, I was trying to make it entertaining at the beginning. I didn't even get into the pumps. So with regard, this is again, just a screenshot, from the software, everything about your piping system, the check valve, the pump. And it's like, so many systems, I'm like, what do you mean you don't have the pump car? Like, what's going on here? They're like, I got pressure, I got flow. I'm like, okay, I can work with that. All right, it's not perfect, but we can input that in the model. Like if you're pumping in series, I love to pump in series. Who's designing systems where you're pumping into series? I got a booster pump and a mainline pump. I'm taking pressure from 0 and I'm boosting it to 2000 PSI. Who's with me? Those are the fun ones. Okay. So pumping in series, pumping in parallel, everything goes into the computer software. In some cases, I'm like, I need a pump bypass control valve or check valve. There's everything about our system goes into the model. The best bet is to have the actual pump curve, and then we create a pump file and add in the pump inertia. I will leave with this note. Who was here during Katrina? Right? So what was the insurance companies like? Replace with the same. So I had a building downtown, and they're like, here's our pump. We're going to order the same pump. They install the pump, started up the pump. It's a good looking pump, good flow, pressure. It's good. They turned off the pump. The building goes, the piping, boom, boom, boom. Like, this system's been working fine for 50 years. What's going on? I'm like, old pumps are great. Lots of inertia. Like in New Orleans Sewage and Water Board, those old pumps are gorgeous, right? Heavy duty, impeller, good. Lots of inertia. New pump, why does this pump weigh half of the old pump? No inertia, okay? So the old school design They were thinking of inertia. They built the flywheel into the pump. All right. So when modeling and looking at the inertia, it's critical of inputting that into the model as you go through in creating a solution to your system. So obviously I could go on forever. So I had a project in Brazil, and in this apartment complex, everybody had their own storage tank and a flow path. And they had horrible pressure transient going in this building that was destroying the building from leaks, and it was then that flow path. We also see that in cooling towers, to make up water in a cooling tower. That valve is critical, and that can create huge pressure transient, which shows it 400 or 500 psi. So it's like control valves matter. Slow down if possible. If you can't slow it down, put in a surge vessel or a damper. Accept that energy. Question. Matter in a part of the water system. How do you control bacteria? So, age of water is critical. So when we look at a municipal water system, part of your specifications would be looking at the liquid level in that tank and the pressure over a course of, say, a week to see if it's cycling properly. I've had many systems that have variable frequency drives on their pumps and pump control valve. So under normal conditions, I'm like, I'm at 52 psi, I'm at 48 psi. I'm not getting any water on that tank at all. So this is where we look at, okay, at midnight, I want you to turn off your pumps. The vessels, when you give energy, can let it work as a pump cycle control. You'll see that vessel drop down to 30%. I like a 20% safety factor in the design so that you're maintaining that water quality and have your operators test it. Now, when I'm looking at an elevated storage tank, it's also critical to all your operating your system. So we can do an extended run of our surge model based on the demand from your water meters, and I want to see how that elevated storage tank is cycling. And if it's not cycling, even with stratification, that's where we'll go into that tank and put in a mixer. So I have a maintained proper, age of water, current residual from the top and the bottom.
Any other questions? No. Oh. Don't roll, Frank. I gotta give you your parting gift. Yeah. Oh, Frank, you gotta come over here. Don't trip yourself. Well, thank you again, Frank. Thanks again for coming and talking to us about surge control tonight. Okay, there you go. I know. Impressive, isn't it? Only the best. Yeah, right. Stick around, have a beer. All right, that concludes our meeting. Thanks, everybody, for coming out tonight.